Hello, my name is Naryung and I'm an undergraduate researcher in the Morehouse Lab. Today, I'll discuss how novel bacterial defense systems can serve as pharmacological targets to combat antibiotic resistance. Antibiotic resistance occurs when bacteria evolve to survive drugs designed to kill them. This is a global health crisis. The World Health Organization predicts that by 2050, 10 million people will die annually from drug resistant infections. One promising alternative to antibiotics is bacteriophage therapy. Bacteriophages are viruses that infect and replicate in bacteria. However, bacteria and bacteriophages are constantly at an arms race, leading to the development of diverse defense systems. Bacteria have innate immune systems, which is the first line of defense against infections. These systems often rely on cyclic nucleotide signaling. For example, CBAS produces cyclic dinucleotides to trigger cell death and stop phage replication. However, phages have evolved to counter this by producing sponge proteins that sequester these signals and shut down bacterial immunity. Recently, my lab has discovered an anti-antiphage system called Panoptes, which detects the disruption in signaling. When phage sponge proteins deplete cyclic dinucleotides, the effector is activated, leading to cellular toxicity. In this way, Panoptes act as a guardian of CBAS and bacterial immune signaling. This leads to the question, can other cyclic dinucleotide producing enzymes be repurposed for a similar defense mechanism? Here we identify Panda, a Panoptes-like dis-A antiphage system. Similar to Panoptes, Panda consists of a cyclase, Pan-S, and an effector, Pan-E. Pan-S consists of a diadenylate cyclase domain found in dis-A proteins, which is responsible for cyclic di-AMP production. My project focuses on understanding how Pan-S functions. First, I aim to solve the apocrystal structure to understand the conformational changes that occur during product formation. Second, I aim to identify key residues required for catalysis. By comparing Pan-S with previously characterized dis-As, we identified a set of potentially conserved active site residues, which we mutated to alanine. Using high-performance liquid chromatography assays, we found that Pan-S activity depends on residues D68, Y85, and R105, as these mutations abolish cyclic dinucleotide synthesis. Current works are focused on solving the structure from the diffraction data collected from crystals. This can lay the basis for the development of small molecule inhibitors. If we can inhibit the cyclase activity and combine phage therapy with small molecule inhibitors, we can suppress bacterial immune responses and improve therapeutic outcomes. Ultimately, understanding bacterial immune signaling opens new avenues for combating antibiotic resistance. Thank you.